Polar air masses are among the coldest on Earth. Their extremely low temperatures are not accidental but result from a combination of geographic location, radiative processes, surface conditions, and atmospheric dynamics. Understanding why polar air is so cold requires examining how these air masses form, evolve, and interact with their environment. Polar air masses originate in high-latitude source regions, primarily in the Arctic and Antarctic. These regions receive relatively little solar radiation throughout the year because of the low solar elevation angle. When sunlight reaches the surface at a shallow angle, its energy is spread over a larger area, reducing its heating efficiency. During winter months, polar regions may experience polar night, a period of continuous darkness that can last several weeks or months. During this time, solar heating is nearly absent, allowing surface temperatures to drop dramatically. One of the most important mechanisms responsible for the cold nature of polar air is long-wave radiative cooling. At night and during polar winter, the Earth's surface emits infrared radiation into space. Because there is little incoming shortwave solar radiation to compensate for this energy loss, the surface cools rapidly. Additionally, snow and ice surfaces have a high albedo, meaning they reflect a large proportion of incoming solar radiation. High albedo reduces net radiation at the surface, limiting daytime warming. This negative surface energy balance ensures that the ground remains cold and continues to cool the air above it through conduction and turbulent heat exchange. Polar air masses are typically characterized by very low specific humidity and low precipitable water content. Cold air cannot hold large amounts of water vapor, and evaporation rates in polar regions are minimal. Because water vapor is the most important natural greenhouse gas in the atmosphere, its absence reduces the atmosphere's ability to retain heat. With limited downward long-wave radiation from water vapor and clouds, heat escapes efficiently from the surface and lower atmosphere. This enhanced radiative cooling contributes to extremely low temperatures, particularly during clear and calm conditions. Another defining feature of polar air masses is strong static stability. Radiational cooling at the surface produces a cold, dense layer of air near the ground. This often results in the formation of a temperature inversion, in which temperature increases with height rather than decreases. These inversions suppress vertical mixing and convection, preventing warmer air from aloft from reaching the surface. As a result, cold air becomes trapped in the lower troposphere. This stable stratification allows polar air masses to maintain their low temperatures over long periods. Cold air is denser than warm air, and polar air masses are therefore associated with high surface pressure systems, often called polar highs. Within these anticyclones, air slowly descends, further reinforcing stability in clear skies. Subsidence within high-pressure systems inhibits cloud formation, which enhances nocturnal radiative cooling. The combination of sinking air, low humidity, and clear skies helps preserve the cold characteristics of the air mass as it moves away from its source region. When polar air masses migrate toward lower latitudes, they often remain relatively cold because their high density limits vertical mixing. They tend to spread horizontally along the surface, undercutting warmer air masses and forming cold fronts. This process allows polar air to retain much of its original thermal structure. Although the global circulation system transports heat from the tropics toward the poles, this transport is not sufficient to fully offset polar cooling. Atmospheric and oceanic heat transfer weakens at high latitudes, especially during winter. Sea ice further reduces heat exchange between the ocean and atmosphere by acting as an insulating barrier. Without significant sensible and latent heat fluxes from open water, polar air masses receive little thermal input from below. This isolation contributes to their persistent cold nature. In summary, polar air masses are extremely cold due to their formation in regions with weak solar radiation, strong long-wave radiative cooling, high surface albedo, low moisture content, and strong atmospheric stability. The presence of temperature inversions, high-pressure systems, and limited vertical mixing allows these air masses to maintain their low temperatures over long distances and extended periods. Together, these meteorological processes create and preserve the intense cold that characterizes polar air, making it one of the most influential components of Earth's climate system. There are a lot more weather curiosities out there ready to be discovered. If you like this kind of videos, we would appreciate if you leave a like and even subscribe to our channel. Your support keeps us going. Thank you for watching.